Alright, so before we start coding with respect to transfer learning, I want to give you a summary of what we've achieved in terms of accuracy and in terms of overfitting with the CovNets. So we use a CovNet, simply 30 epochs. Then we use CovNet plus dropout, 30 epochs. CovNet plus data augmentation, 30 epochs, and also 100 epochs. And then CovNet plus dropout plus data augmentation for 30 and 100 epochs. And this is the accuracy numbers that we got. You see that adding dropout actually brought the accuracy down, but both are overfitting. From very early on, epoch 5, we start overfitting. Then when we added data augmentation, actually the overfitting disappeared. So it seems that in this case, data augmentation had more effect on fighting the overfitting than dropout has. Albeit that we used 50% for dropout. So you see also that going from a 30 to 100 epochs also improve the accuracy of our validation. So here you see 83, and when we use dropout and data augmentation, we basically reached 85% accuracy without any overfitting. Alright? So next what we're going to do is we're going to use transfer learning. So we're going to borrow the convolutional base of an existing CovNet. We will use ResNet as mentioned. It's basically ResNet 50, meaning the first 50 layers of ResNet. But we will also show you what the results are for another CovNet, VGG 16. Because this is what Francois Chollet used in his book, Deep Learning with Python. And so we will fill these out as soon as we have the results. But before we get to coding, I just want to highlight two things. So we will deal with transfer learning. Transfer learning means we're going to use a pre-trained CovNet, like ResNet 50 or VGG 16. And here we had two methods, feature extraction and fine-tuning. We've not seen fine-tuning yet, so we exclusively deal with feature extraction. But there's two methods, and we're going to use both methods. Method one, so we have our pictures, color pictures of 150 times 150 times 3. And we're going to run these through the convolutional base. And we're going to use the weights of ImageNet. That gives us a feature map of about 5 times 5 by 2048. So 2048 is actually a quite deep feature map here. And what we will do is take that feature map and create a NumPy array. And that NumPy array is samples times 5 times 5 times 248. So the only thing we add here are the samples. For example, for our training set, samples would be 2000. So if you reshape that array and you flatten it basically, then you get an array of, in our training sample case, 2000 and 51,200 columns. 51,200 is 5 times 5 times 2048. Now this array, so this is still an array. This is still a NumPy array. This will be fed into a fully connected layer, of 256 units. And then this will be fed into a sigmoid layer. So basically our model starts here. We only have 2 layers. The nice thing about this is that this method is fast. You just loop here for the epochs. But the disadvantages are that you can't use data augmentation in this technique. Alright? Now the second method is a bit different. Yeah? So we still have our input, but here we're going to have 4 layers. This is layer 1, layer 2, layer 3, layer 4. So this is going to be, convolutional base is going to be a layer. We're going to do layers at convolutional base. The flatten will be a layer, because here we just did a reshape of an array. But here you have layers. Fully connected is a layer and sigmoid as well. So these two we also have there, but these two are fundamentally different from these. The nice thing about this is it will allow you to do data augmentation, but it's going to be slow. Because of course your epochs are going to go through these 4 layers. And because you're going to go through the 4 layers several times, we need to freeze. We need to freeze these. Yeah, so we're going to have to freeze the convolutional base, because if we use the ImageNet weights, we don't want to adjust the weights every time we run an epoch. Here you don't have that problem, because the pictures will only see the conv base once, and here are also ImageNet weights. From there we have a feature map that we convert into an array, and we feed the array as the input in this fully connected layer. So you look here, yeah? So no need to freeze the base here, but here you need to freeze the base. Alright, let's start our transfer learning coding sessions.